My name is Erica Gambatis, and this is my case analysis. So for my case, an athlete was preparing for the Summer Olympics, and a random drug test was performed. So I performed a screening test in lab, and that screening suggested that there was a presence of amphetamine. So here is the results from the screening test. Right here you can see the column for amphetamines, and if it was a negative result, there would be two clear lines here like all the other drugs showed, but there was missing a second line. So the test was positive for amphetamine, and here is a comparison of my dipstick test compared to all negative results. So right here you can see the two lines missing a line here, so that is a positive result for amphetamine in the screening. So because there was a positive for amphetamine in the screening, one of my objectives is to extract amphetamine out of a urine specimen using solid phase extraction for further analysis on an instrument. That instrument I chose is LCMSMS to verify the identification of amphetamine in the urine specimen, and then to quantitate the concentration of amphetamine using a calibration curve with controls and calibrators. Okay, so for my case interpretation, this is a case of forensic urine drug testing because the urine is getting tested for the Olympics, and they do urine testing to test for drugs. My drug target is amphetamine at 150 nanograms per milliliter. So a little bit about amphetamines is that they act as a stimulant. There's the D and the L in enantiomers, which could be important for certain testing, like workplace testing, because the two enantiomers, they have different effects, and one can be prescribed. So amphetamine can also be prescribed for ADHD, obesity, and narcolepsy. So pharmacokinetics of amphetamine. The pharmacokinetics are essentially the same of methamphetamine. They're lipophilic, so they really like lipids, and they're well absorbed, and they have a volume of distribution of about 3 to 5 liters per kilogram. They have a really large half-life range of about 7 to 34 hours, and they're metabolized in the liver via aromatic hydroxylation. And that half-life range, that's dependent on the pH of the urine. So based off if it was acidic or basic, because amphetamine is a basic drug, acidic urine, it's going to be ionized, it's going to go out of the urine faster, so it'll be excreted faster and have a shorter half-life. And then also amphetamine pharmacodynamics, so it's a neurotransmitter reuptake inhibitor of the neurotransmitters dopamine, norepinephrine, and serotonin, and it inhibits metabolism of neurotransmitters. So these two combined just are elevated signaling a lot of neurotransmitters in that synaptic gap, which was going to result in the rush. And then because it's a reuptake inhibitor, it's going to then result in a crash. And then also amphetamine is a basic drug. So these are my parameters for the calibration curve. So like I said, amphetamine at 150 nanograms per milliliter. And then I'm going to add an internal standard deuterated amphetamine at 150 nanograms per milliliter. And then calibrators 1 through 5, all at units of nanograms per milliliter once again, 10, 100, 200, 300, and 400. And then a QC at 200 nanograms per milliliter. So these are the procedures. Like I said, the internal standard is going to be deuterated amphetamine. So I'm going to use solid phase extraction for the sample prep in a polymeric cation exchange cartridge. So these cartridges are made for drugs who will get a positive charge when they're ionized, which means that the cartridge is negative charged, so that when the drug is ionized, it's going to stick to the cartridge. So to do this, I'm going to make the urine acidic, basically just the pH 2 below the pKa. The pKa of amphetamine is 9.9, so the pH is going to be less than 7. And by making it acidic, it's going to ionize the amphetamine that's present in the urine and make it a positive charge, a cation. So then I'm going to condition the cartridge with methanol, water, and a sodium acetate buffer. So water will create air pockets, so the methanol makes sure that those air pockets aren't created. Then the water is going to wash away that methanol, and then the sodium acetate is going to make sure that the amphetamine maintains its positive charge when it's going through. And then So then I will extract all the calibrators and controls in the unknown through the cartridges, wash that out with water and methanol because those are neutral, and then when I want to elute them out of the cartridges, I will use 2% ammonium hydroxide and acetonitrile. This is really basic, so it's going to make the amphetamine go back to its neutral form, no longer will be positive charged, no longer will want to attract to the cartridge, and it will elute out. And then when it's collected, I will add methanol and a hydrochloric acid mixture to make sure that the amphetamine then goes back to an ion form, so that when it's evaporated, the amphetamine does not get evaporated with the solvent because amphetamines easily evaporate. So then I will evaporate in a turbovap and reconstitute it in acetonitrile and methanol for analysis on the LCMSMS, and then use the acetonitrile methanol blanks. So one of my parameters is the interference studies of matrix interferences. So an overall definition of interferences from the SIDC document is that non-targeted analytes that might affect how an analyte of interest is detected, identified, and quantitated. So matrix interferences, these are just like those non-targeted analytes, so things that we don't want to see in the biological specimen, and in this case that is urine. Basically a suggestion of how to resolve this would be to analyze 10 Blake matrix samples without internal standards from at least 10 different sources to detect common matrix interferences. So basically collect 10 blank urine samples and see what interferences might be present within them. And then for internal standard interferences, internal standards can actually interfere in two ways. So the first one is that when you get that deuterated internal standard, it might have some impurities in it, and it could actually contain the non-labeled compound, so that is the analyte of interest that you're looking for as an impurity. Also, deuterated internal standards, when they're run through the mass spectrum, they're going to produce fragments, and sometimes those fragments can be the same as the analyte of interest fragments, and they might have the same mass to charge ratio. So this is how to prevent these two interferences with my case specifically. So I would take those 10 blank urine samples, each from the 10 different sources, and I would extract them using the solid phase extraction used before and analyze it on an instrument. And I would do this without the internal standard present within them. And then once I analyze those on the instrument, I would make sure that there's no interference at the retention time of amphetamine on the chromatogram. So the same retention time of amphetamine, make sure that there's no interferences at that time. And then for the first internal standard interference that can occur, I would randomly select one of those blank urine samples, and then I would add the deuterated internal standard to that blank, and then I would extract it using the solid phase extraction and then analyze on the instrument, and then once again make sure that there's no interferences at the same retention time of amphetamine on the chromatogram. For the second part of interference studies, I would randomly select one of those blanks once again. This time I would add an amphetamine standard at a really high concentration, so at the upper limit of the calibration curve, and then I would extract that using solid phase extraction, and then I would analyze it on the instrument, and then this is without the internal standard present. So when I analyze it and I look at the mass spectrum, I'm basically just making sure that none of the fragments have the same mass to charge ratio that the internal standard did. Okay, so this was the class I was this was the question that was presented to me from class. So this is how I would explain it to a lab supervisor. So when a sample is collected, it's collected, labeled, and packaged, and then it's prepared to be sent to a crime laboratory. So depending on the specimen, it might have to be refrigerated or kept at a certain temperature to make sure that it's not altered. So then it is transported to the crime laboratory, and it could be transported either by like hand or mail delivery. So then it gets to the crime lab, and usually an evidence technician will obtain the evidence, and it will bring it into evidence storage, and it will be stored at an appropriate temperature, once again depending on the specimen or even the drug present within the specimen. So then once it is in storage, if a toxicologist is ready to test it, it will they will go down into the storage and they will request to take it out of storage, and then they will bring it back for testing. They'll perform a screening test and then a confirmation test, and then they can bring it back into the storage room with the evidence technician. And then a lab supervisor can go over the testing, make sure that everything was correctly done, and make sure that the testing was all done according to standard operating procedures. And then from there, the evidence technician will be notified that the sample is no longer needed, and then it will be stored for long-term storage, which is usually means that it will be frozen. And from there, then we are making sure that every single step was documented correctly. So basically, from the time that the specimen was collected to the time that it got brought into long-term storage, every single step of every single person who touched the evidence is documented, with their name, with their time, and with the date that they had it. So every time that evidence is touched by a different person, that is documented in a chain of custody report. So if anything goes wrong, like, we know exactly who was in possession of that evidence at the time. Okay, so then this is how I would explain this in layman's terms during a courtroom testimony. Okay, so when a sample is collected from a particular person, then that sample can be taken and it will be collected properly and then labeled, and then it will be packaged and ready to be sent to a crime lab. So someone will take this evidence from a particular scene to the crime lab, and it could be either sent through the mail or hand delivery. And then when it gets to the crime lab, usually an evidence technician will obtain it and put it into storage. During the transportation of it, and while it is in storage, it might need to be kept at a certain temperature to make sure that it's not altered or anything changes to it. And so then it will be kept in storage. When a toxicologist needs to test it, they will go to storage and they will take the evidence, and then they will bring it back for testing. They will do a screening test, which means that they will first test to narrow down what might possibly be in the sample that they received. So the sample could be something like blood or urine. They will test to see what type of class of drugs there might be, so they're basically narrowing it down to a particular group. And then from there, they can do a confirmation test, and the confirmation test will confirm exactly what drug or something else was in that sample and exactly what concentration or amount was in there. So then when they are done, they will take that evidence back into the evidence collection room, and a lab supervisor will go over all of their testing, everything, to make sure that they did everything correctly and up to protocol. So then from there, then the technician can be notified that the testing is done, and the technician can make sure that that evidence goes into long-term storage, which would be like freezing it, just to make sure that it's preserved for the certain amount of time that the lab requires it to stay there. And throughout this entire process, everything is documented. Whoever is in possession of that evidence, that is documented, their name, their time, and their date. So if anything happens to go wrong, we would know exactly who was in possession of that evidence at that particular time. And we know exactly who had that evidence throughout the entire time that it was collected and then put into long-term storage. And then these are my references.